Hello and welcome to our presentation on how to perform root cause analysis on inaccurate prediction models. My name is Oscar and I'm a software developer at Verifyter. The theme of our presentation sprung from, well, as you can imagine, setbacks. Paper details our journey and conclusions on how to debug an ML implementation, infrastructure and all. In the presentation, I will brush on some of our main points and hopefully invoke your curiosity to develop on these ideas and perhaps find some helpful tips along the way. To set the stage of where we were at when our problem started compiling, we had our intended features implemented, gathered training data, and produced a decent model. Everything seemed in place, but the predictions generated when running were of no help. So, pulling our hair trying to figure out if the projects we were running on were in any way exceptional, or if something completely unpredictable had happened. Did our implementation contain a bug? This presentation is our lessons learned on how to debug ML. So why is debugging an ML implementation any different? In the upper graph, you have a healthy range of values. However, in the below graph, during live inference, we expected to see similar prediction values. This is the distinction between conventional bugs and ML bugs. There is no direct pass or fail criteria. An ML bug is a performance bug. Well, before we delve into that, some background information on how pin-down works is in order. I'm sorry for this short interlude, but Daniel is very fast in explaining how our tool works.
Debug is by far the largest task for ASIC verification engineers, and the problem is getting worse. The largest and most boring part is debugging regression failures, but you can automate this using pin-down, which is an automatic debugger of regression failures. How does it work? Step 1. Pin-down tries to predict where the bugs are without running any tests. Step 2. Pin-down tries to fix the bugs and make sure the tests pass again. Step 3. Reporting. A test is failing. It used to pass. Since then, 9 changes have been committed. Which one contains the bug? Step 1 is prediction. How complex is the code? Some changes are complex, some are not complex. This is a feature. A feature is a measurement of some aspect of the code, people, or organization that has some predictive power. Pin-down has more than 100 features to choose from. This is a heavily researched area. We have used machine learning to train pin-down to recognize bugs. Machine learning requires a lot of data. Data on real bugs is extremely hard to find, but luckily pin-down has generated loads of bug data which we can use. The result of the machine learning is a bug prediction model. Now back to the example. Using the bug prediction model, pin-down sorts the commits in bug probability order. Step 2. Validation. All changes made in commit 5 have now been removed. This was done locally, nothing was committed. Notice that up to this point no tests have been run. Very little time has passed. However, now pin-down is going to compile and rerun the test on the remaining code. The test passes, which proves that the bug must be in commit 5. Step 3. Reporting. We have the revision and commit message, the failure, the bad code that caused the failure, and the report is assigned to Daniel.
Thanks for that insightful presentation, Daniel. Now the key point. Predictions are used to rank commits by risk without running any simulations. As mentioned, our initial implementation didn't work, and that resulted in a lot of time spent debugging. We condensed our methodology into a workflow. Starting off with identifying if there actually is a problem, our workflow is constructed in such a way as to minimize the cost of finding the potential error. In a sense, each step contains 2 points: how to identify a problem and what you should keep in mind when implementing to make future debugging easier. The prediction values, being the output of the models, are the starting point for debugging. If something is wrong, this is where we'll notice. The next step concerns itself with the models, and this step contains a key piece of implementation advice in the name: models, plural. Although some information regarding the features can be extracted during the previous step, an analysis of the features is our next step in the workflow. This is the first intrusive step that requires access to information from the live environment the model is predicting on. Finally, we'll end off by having a closer look at the labels used in the dataset. Although analysis of the training data is a must before even creating the model, this is our last point in the workflow and requires the most manual work. So, how do we know if something is wrong? The issue here is that a single prediction isn't a clear indicator of whether there is a problem or not. As we expect to see a bug once every 45 commits, and the bug ranked first 40% of the time, we need some time to pass before we can say conclusively that the model isn't working as intended. The takeaway here is that during training, when the model is validated against the validation set, save the prediction distribution for later comparison against live inference. Let's frame the difference between a conventional bug and ML bugs again. In traditional code, Boolean-based logic can uncover a bug, whereas the black box probabilistic nature of ML is more akin to a performance bug. The reason for saving the prediction distribution from the validation set is that as live inference samples drop in, we can compare the two distributions. Fun fact, when the Irish invented whiskey in the 1400s, it took another 300 years before they made any notable inventions again. Although, much later, one such invention was the student's t-test, used at the Guinness brewery to determine statistical differences in crop yield. We use the student's t-test to determine if two prediction distributions are in fact different. If we observe a difference between the validation set's distribution and the distribution generated during live inference, we have our first sign of trouble. Although it's not complicated to implement, student's t-test is such a common tool that it exists in most statistical libraries. Now, I know what you might be thinking. Oscar, as the sample size grows, the t-distribution approaches the commonly known normal distribution. And that is true. Student's t-test is only used on distributions that are expected to follow a normal curve. For non-normal distributions, the Mann-Whitney U-test is better. Except applicable region, the main computational difference between the Mann-Whitney U-test and the student's t-test is that for the student's t-test, you need to save the values needed to recreate the distribution, i.e. mean value, standard deviation, number of samples, min and max values. Whereas the Mann-Whitney U-test uses each sample from both datasets to make a comparative judgment, i.e. all values from each dataset need to be saved. Using prediction scores to identify if there is a problem or not can, in most cases, be done visually, without any specific tools. At least in the beginning of a project, implementing statistical checks along the way is quite cheap, as minimum implementation effort is required. In the report, we mentioned that Google wrote a paper on statistical significance testing to find errors, and I think their conclusion is worth mentioning. At a certain scale, significance testing is too sensitive. This is a problem we've noted as well. But in our use case, to identify the first signs of trouble, it's worked fine. The predictions give us an idea of whether there is a problem or not, but it doesn't necessarily tell us where the problem might lie. As I mentioned earlier, models plural is a key piece of advice when trying to debug inaccurate predictions. We've built several models with different purposes. When generating a new model, we initially set out to use as distinct features as possible with the most predicting power. This main model is used in the debugging pipeline. Alongside that model, we create another set of models, not always as good during training, but still with the aim to act as good predictors. The difference lies in which feature subset we use. These models that are running in background are placed in so-called shadow mode. They perform their predictions but have no actual effect on the tool's decision making. The difference between our version of shadow mode and the ones used in the car industry is that when a shadow model predicts a different course of action for the car and that action is not taken, there is no way of evaluating whether it was the correct decision or not. Whereas in our case, all predictions made are in a sense safety caged within Pindown's validation mechanism. We know after the prediction which choice was correct and which wasn't, meaning that we can swap the worst performing model to the best performing model. If only some models act differently when running live, the error might be within the feature subset used in that specific model. However, if all models perform bad, the root cause might be a discrepancy in generating live features versus those generated when creating the training dataset. Whether it's a systemic problem between training and live feature generation, or just a couple of features misbehaving, the next step is to take a closer look. We've identified 3 techniques that have helped us along the way. Statistical distribution checks, similar to those used when comparing prediction scores. However, this time we're comparing the features live versus training. This requires access to the features generated when running live, so our implementation advice is to store this either in a generated file before each prediction or in a database that you have access to. Our next step is value range assertions. This step requires some domain knowledge, but it's cheap to implement and catches potential errors. Finally, we have our logical interfeature assertions. These two require domain knowledge and some thinking, but have been proven to catch bugs early in the development process. If, like us, there are no libraries of data to be found online to train your models on, then you have to generate the training data and label the datasets yourself. There is a chance that some assumptions have to be made, and there might be interdependencies between samples that change over time. These are implementation choices that you will discover along the way, and it might affect the generation of training data in one way and the live prediction features in a different way. To catch these implementation errors, we've resorted to a general overview of discrepancies by statistical difference testing. Value range assertions are cheap to implement. If you know the range within which a feature can assume, you can place traditional value checks to see that these are not broken. Since the training data is a larger sample than the live frames, we can almost be certain that the features when running live should range within a given set of values. If the live frame deviates from that range, this sample might be a bug. But it could also have captured an interesting point on which to study further. If you look at the graphs below, you can see that the training data has the majority of samples below 1. The live frame never assumes that value range. This was a bug that we had missed when scaling timeframes on historic data. Assertion 3 concerns itself with inter-feature relations. This assertion requires some planning, but they're extremely beneficial when catching implementation errors early on in the process, although they should be used with care, since this is an area where human bias might be projected on the dataset. The example given, more files edited than number of lines, sounds logical, but in some revision control systems, metadata, such as read and executable rights, can be stored, but these do not entail updated lines of code, as the assertion expects. If no obvious implementation errors have been caught as of yet, our next step is to revisit the labels used during training. As you all know, machine learning leverages on large quantities of data. Labeling datasets can be an arduous task. To save time, automation is key. Now, as previously mentioned, Pindown validates the proposed bugs by rerunning the tests that failed to see that the removal of the predicted revision will make the test pass again. This means that the revisions labeled by Pindown only contain true positives. As Pindown runs on a project, more and more of these bugs are stored in a database to be collected later when generating the training data. However, if for some reason the project that is running Pindown is put on hold for a short period of time, there might be gaps in the timeline of bugs. Or perhaps the project decided to continue development without using Pindown at all, only to resume using it closer to a deadline. These two scenarios can be difficult to discern. And what do we do with these chunks that have no validated bugs? Is there a chance that these gaps contain bugs? Well, yes, obviously they might. This is a very difficult problem. If the training set contains false negatives, i.e. samples labeled as clean but are actually bugs, then this has the potential to skew feature importance during training, or in worst case, inhibit generalization altogether. This is why, when generating the training set, we try to use as many different techniques as possible. Mining software repositories is a large conference that concerns itself with, well, as you can imagine, retrieving information regarding projects from the revision control system. Among others, bug prediction is a heavily researched topic. If you ever found yourself sorting through issue reports, you may notice that a large portion of them are not actually bugs. With the help of MSR Conference, we've found multiple techniques to retrieve the bug label. On the slide, you can see, as I mentioned earlier, gaps in the timeline where no bugs are present. The graph below, however, contains no gaps of this size. It is also worth noting that the below graph has a higher frequency of bug labels as well. Automation is key to generating training data. If the training data can be done by hand, you are probably in a situation where the amount of data is insufficient, or you've managed to hire extremely dedicated people that deserve a raise. Spend some time to identify the pros and cons of each technique and use this against each other. If one technique erases false positives and another erases false negatives, you have the beginnings of a very good dataset. Performance bugs are innately difficult to trace. This is because they usually don't result in an error. Our first piece of advice was to set up a way to identify if there are any discrepancies between live and training predictions. Statistical significance testing is a decent method. Although too sensitive in some cases, it's a good finger in the wind. If there aren't any discrepancies, the model you've deployed will most probably work as intended, however poorly that may be. Our next step was to train multiple models with different feature subsets. This can help you identify which feature groupings are performing badly, or if there is a deeper problem. When looking into features, we had 3 different techniques. The earlier mentioned statistical significance testing, value range assertions, and logical interfeature relationships. This step requires some thinking and care, so you keep human bias to a minimum. Finally, we recommend that multiple automated labeling techniques are used. Identify their strengths and weaknesses to make the best possible dataset. Remember, the key to a well-performing prediction model is a clean and healthy dataset. This can require a lot of work and is no easy task. Hope our story on how to tackle the problem of debugging an ML implementation is of help to you. Now enjoy our workflow. Thank you all for listening.